So we're going to chat about the regulation of the urine concentration. So this regulation happens in juxtamedullary nephrons. Okay, so this is a typical juxtamedullary nephron here. The white part is called loop of Henle, or nephron loop. And this red part of capillaries is called vasa recta. Vasa being vessels, recta being straight vessels. So this whole system is called countercurrent exchange system, meaning that the filtrate and the blood kind of go in sort of opposite ways, to some extent. We'll talk about it. So loop of Henle is called countercurrent multiplier. Vasa recta is called countercurrent exchanger. Now, let's talk about what happens there. All right. So this is proximal convoluted tubule, distal convoluted tubule, collecting duct. This is loop of Henle. Right about here is the boundary between cortex and medulla. Okay. So I'm going to set up some environment here. Turns out that the osmolality, remember what osmolality is, it's a overall concentration of stuff, right? So it turns out that osmolality of interstitial fluid, extracellular fluid, in medulla increases. So it's about 300 milliosmoles here. We don't need units. We don't just numbers, and numbers, look, numbers are more for illustration purposes. I'm not going to ask you to memorize those. And it rises to 1200 here. So remember, it's how concentrated this stuff is, right? So when filtrate comes in here, filtrate is at 300. Ballpark. So it goes in. It's in balance, right? Everything's fine. Now let's say somewhere here, the concentration becomes 600. And this is why I hate to talk about this. We're talking about it as step-by-step process. It's a freaking flow. It's not step-by-step. It's continuous. You see what I'm saying? But let's say we take a snapshot what's going on here. Filtrate is supposedly 300, but outside of the tubule, the concentration is 600. So the concentration of whatever is much higher outside of the tube than inside of the tube, than in the filtrate. So remember, water would go to the higher concentration of solids. So water is being reabsorbed throughout. Does that make sense? Are we clear?
Yeah.
So here, it's called descending limb of the loop of Henle, descending limb. Reabsorbed via osmosis, so it's passive reabsorption in the descending limb. We good? Now, as water is being reabsorbed in the descending limb, what happens to the osmolality of the filtrate? It increases. Very good. So here at the bottom, it ultimately, and look, it it always, water is being reabsorbed to the extent, to the concentration that's outside. So ultimately the highest is 1200. So filtrate becomes also 1200 at the bottom, right? The highest concentration. Now what happens to the volume of the filtrate?
It would be decreasing.
Yes. So we're going to put, I'm going to use different color just to highlight. So this is V1 here, okay? This is V2, and this is V3. Does that make sense? So we can write down, check this out, that V1 is more than V2. Am I clear? And substantially more. Now, as filtrate goes up, now look what happens. It goes from high concentration to the low concentration. Does that make sense? And what happens here? At each step, the concentration of sodium in the filtrate is a little bit higher than the concentration of sodium in the medulla. So sodium chloride is being reabsorbed. Okay? Now,
Always sodium chloride, or it depends what?
Mostly. There is some urea. We'll get to the urea a little bit later.
So it's always sodium chloride no matter what, like we're talking about, that's in the filtrate.
Yeah, sodium chloride is the primary thing here. And for sodium, it's going to be both passive and active. So there is diffusion and there's active transport. Does that make sense? As now, to kind of spoil it well, there's also a secretion of urea in the filtrate. So all of it kind of, creates that hyperosmotic environment. Now, as sodium chloride is being reabsorbed in the ascending limb, what happens to the concentration of the filtrate? Osmolality of the filtrate, so to say.
Sodium chloride is being reabsorbed?
From the filtrate into the extracellular fluid. It's taken out of the filtrate.
Okay.
So osmolality
Decreases.
to 100. Okay? Does that make sense? Awesome. So, how do you think V2 and V3 relate to each other?
V3 would be less than V2.
Same extent less as V2 versus V1? No, because obviously water contributes to changes in volume much more than sodium chloride. So we can put something like this. Less or equal. Well, kind of, a little bit less-ish, small-ish. We clear? Awesome. Now, what happens next? This 100 milliosmoles filtrate gets into the collecting duct. Now, first of all, check this out. We generate roughly, I think, 120 liters, or 180 liters of filtrate a day. But due to this, we end up peeing out like 2 liters of urine, or less, right? So, in the collecting duct, there's also water reabsorption. Because, look, it's 100 here, but the concentration in the medulla is 300. Does that make sense? But this time, and this is critical, So this water reabsorption in the collecting duct, it's passive. So but by osmosis, you know. But it uses special channels called aquaporins. So far makes sense? The biggest difference between reabsorption in the descending limb and the reabsorption in the collecting duct is that this reabsorption is obligate, meaning that it's going to happen no matter what, while this reabsorption is facultative. Are we clear? What makes this reabsorption facultative? Imagine that you have very low, no. You have high osmolality of the plasma. Does that make sense? Now remember what it triggers. It triggers the release of a hormone. I don't know if you remember the name. ADH, antidiuretic hormone. And this hormone, also known as vasopressin, look what happens. It increases the number of aquaporins. Cool? Increased facultative reabsorption, increased urine concentration. And, of course, reduced plasma osmolality. Does that make sense? Let me just walk you through. So, your plasma, say, you're dehydrated. Osmolality in the plasma goes up, triggers the ADH release from posterior pituitary. ADH simply increases the number of water channels. So more water can passively be reabsorbed. Does that make sense? Which means the concentration of the urine goes up. You produce less urine and it's very concentrated. Does that make sense?
Yeah.
You pee a little and it's like dark brown. Well, maybe not dark brown, but kind of darker because it's concentrated.
So is what's coming out of the collecting duct
That ultimately urine.
urine?
Yes.
And plasma is,
It's just blood. Just response to blood.
and blood is like what's, when you're saying like 600 or 1200 on the, yeah.
Well,
Is that,
technically it's interstitial fluid, yes.
okay.
But blood and overall interstitial fluid are very connected. So changes of the concentrations in the blood are reflected in interstitial fluid, yes.
Okay,
Does that make sense?
yes.
Okay, awesome. So obviously if plasma osmolality goes down, we flip everything, right? Does that make sense?
Mm-hmm.
Now we have to deal with one problem. So far, this mechanism of reducing the volume of the filtrate and returning stuff back, does it make sense?
Yeah.
So, few details. What maintains the gradient of concentrations in the medulla? Mostly urea, okay? So what essentially happens when there's a urea reabsorption here. Urea is being actively pumped into the filtrate from the blood because it's a product of protein degradation. But then urea will move from the filtrate into the medulla following that difference in concentrations of the filtrate. So filtrate is very concentrated here, more concentrated than medullary tissue. So it will move here, and as water being reabsorbed from the urine, see this here? Urea concentration will go up in the urine, and that will drive the reabsorption as well. You have a cycle basically, okay? So urea being moved into the filtrate somewhere here, but then taken in the ascending loom in the ascending limb and collecting duct back into the medullary tissue. Does that make sense? Now I'm trying to think about... Oh yeah, we forgot. If you will be reabsorbing water, this whole gradient of concentrations in the medulla will go to shit. So you need something else that would pick up all the water. Does that make sense? And that will be this vasa recta. Okay? Does that make sense? So it will essentially, you will have blood getting in, right? And blood getting out. It's a really poor drawing, I know that. But here's the thing. If you remember the order of blood vessels in the nephron, look at this. So you've got, check this out, you've got afferent arteriole, efferent arteriole, vasa recta, postcapillary venule. That make sense? So this is kind of interesting. So the blood goes into the vasa recta from efferent arteriole here. And blood leaves vasa recta into postcapillary venule. And you have two volumes. You have, let's call it volume 1 here, and you have volume 2 here. So here's my question. Which volume is bigger, 1 or 2? Which is bigger?
You said the
blood picks up.
vasa recta reabsorbs the water.
Yeah. So blood enters from efferent arteriole, goes through the vasa recta, goes back into circulation.
And picks up water.
Uh-huh.
So the volume would be greater
At the
at
exit.
the end.
Yeah. I hope it makes sense. Now, there are a few things that are kind of interesting here, and this is why I like renal system. Ramifications of physiological changes are just enormous. So think about this. ADH, right? Another term for ADH is vasopressin. We talked about ADH, I'm kind of summing it up. Vasopressin. It is vasoconstrictor. Does that make sense? Remember this afferent arteriole? Well, when vasopressin goes up, it's vasoconstrictor, so afferent arteriole will constrict. If it constricts, how does it change the blood flow through the glomerulus?
Decrease.
It goes down. As it goes down, how does it change GFR? Decreases. Less GFR, less filtrate. Less filtrate, more water is being kept in. Additional effect to reduce plasma osmolality. Does that make sense? It's not just through the increased facultative water reabsorption. ADH increases thirst. So you're simply drinking more water if you're dehydrated. Does that make sense? Now, we technically, now, like, the only thing that we should do next time, we should overview, I don't really know if we need to overview the reabsorption of ions. Well, we actually kind of do, so what we're going to talk about next time, we're going to chat about the regulation of sodium reabsorption, which is aldosterone and ADH. We already covered potassium. We say a few words about calcium, and we say a few words about the regulation of acidity, alkalosis, acidosis, and that'll be it. Any questions? Awesome.